So I'm going to just take a few minutes, not a very long presentation, talk about a different application that actually is very suitable for sound check. Basically, we're talking about haptic. Haptic is basically a feedback on something that you touch, and instead of, say, pressing a button, it feels like you're pressing a button, but it's actually a vibrator or a linear motor that's doing the shaking. It makes it feel like you're touching a button, but it really isn't. So anyway, that type of application is what we call haptic. And most common device or transducer or actuator that's used today is called a linear motor or a linear actuator. In fact, the proper name is linear resonant actuator. So we'll talk about how that works. So the English term haptic, what does that really mean? It's actually from the Greek word haptikos. It means pertaining to the sense of touch. So the applications we're talking about here is really, like I said, touching a surface of a device, and by pressing on that surface, it vibrates to a point where it gives you feedback, makes you feel like you actually pressed the button, even though there's no button to press. It's the vibration that's giving you a sensation that you touched or pressed a button. So recreates a sense of touch by applying a force or vibration to the motion to the user, your fingertip usually. And it could be something else. And it feels real, even though it's not. Steve was using an iPhone 7 earlier for his demonstration. In fact, that iPhone 7 in the front has no buttons. But when you press what normally is a button, it feels like you definitely pressed the button, even though there was no button there. And that's created by a linear motor. So talk about a little bit about the history. The early haptic applications, a very common one that some people might know is if you're flying an airplane and the pilot has the controls, and when it's about to go into a stall, it actually shakes that control to kind of let the pilot know something is going on very badly. You need to fix what you're doing. And if you're young enough and you still go to the arcade sometimes to play video games, let's say you're on a motorcycle racing game and you're going to the corner, that handle will actually shake. It makes you feel like you're going around the corner and there's a vibration. So that's a very common usage, is also video game feedback. And in fact, in the consumer electronics world today, there are many applications such as computers, smartphones. I talked about iPhone. There are watches, the iPhone watch, or Samsung I think also has similar. And something new, virtual reality headsets. There are also a lot of haptic feedback in that kind of device now. So essentially, it has a large screen, but you can get this tactile feeling of like a keyboard, like a regular keyboard when you're typing on it. So the early haptics for consumer electronics, really it could be something like a Motorola flip phone. And I also remember something like this. I'm old enough to know that when these came out, they were the best phones available. Very small, very compact. They fold closed and open. And when they tell you there's a message or a phone coming in without making a lot of sound, it actually has what they call an ERM, an eccentric rotating mass. It's basically a DC motor attached to a small mass that is eccentric. So it's not a complete circular cylindrical mass. It actually has a notch in it. So it's off balance. And when that DC motor spins with the mass attached to the end, it shakes. So it has a very strong resonant frequency, so strong it vibrates the whole device. And because it's a DC power motor, you can't really control the amplitude, how much it shakes. Basically, you turn it on, it shakes it the way it does, and that's it. And it has a very high power usage. So it takes a lot of lot of battery power to run this ERM. So the ones today, the haptic technology today, it combines natural touch, vibration, sound, and real-time surface deformation. So these are different types of technologies that are available. Not just the linear actuator, but there are other things that are also available, and I'll just quickly review those. And basically, it has a meaningful feedback based on the touch action. So if you touch something, it will give you feedback based on the pressure or whatever your part of your body is touching that surface. So something like a Apple, computer here, the newer MacBook Pros, actually has 4 sensors underneath the surface, and it gives you feedback based on the force it senses on that particular surface. And the actuators created a feedback based on that. And also it could be an acoustic feedback. So now this is one we see a lot of, at least in the US, it's very famous now. It's called the taptic engine. So instead of haptic, it's taptic. And that's just an Apple term for the same thing we've been talking about. And it's actually available today in the iPhone 6s, iPhone 7, the iWatch, the MacBook Pro, and it has the pressure sensing 3D touch. So here are the 4 sensors, and under here is a linear motor. It looks like this. And what's interesting here is we're actually not sensitive to which direction the vibration is taking place. So let's say the shaking is perpendicular to our skin. We can actually tell if it's perpendicular or lateral. So in fact, we figured out that when the vibration is lateral to the skin, it doesn't take as much intensity to feel the same as the perpendicular action of the vibration. So that's why these Apple linear motors are actually lateral to the surface that you're touching, not perpendicular. It actually takes less energy to run it that way. So this is a different kind of actuators for haptic applications today. First one is the eccentric rotating mass, the ERM. I talked about the StarTech phone. My iPhone 5S is actually not that old. It's maybe 3 years old. It actually has the ERM in it, in this one. It's just a very small one at the very top of the phone. Very tiny little one. There are things like piezo ceramic, which actually is a specialty material that when you conduct electricity to it, it will change shape and at very different frequencies. Some very advanced material called electroactive polymer, where if you conduct electricity to that, it will actually change its shape, and it's pliable. It's not rigid. The piezo ceramic is actually a pretty rigid material, but it has also a vibrating action when you apply voltage to it. And then the one we're really interested in is the linear resonant actuator, or linear motor. It's the LRA. So that is actually the one that's very, very common today. Lots of smartphones have the LRAs in it. So the ERM we talked about, there's an off-center mass attached to a DC motor. And because it's just really, you can't really control it, the vibration is omnidirectional. It's the entire device will shake. And you can't really control the amplitude, so you can't create this sophisticated feedback. There's no profile that you can create. And you can't control, basically, how much it shakes. It's inconsistent, it's not precise. It is cost effective because it's a very simple design. It's just a motor attached to a spinning mass. So this the piezoceramic material, so when you attach a voltage or you connect a voltage to it, it will bend its shape. So going from a flat surface to a bent surface. There's actually, here's a relaxed state which is flat, and then this is transformed state. It's very, very thin. It could be less than a single millimeter thin. And it could be multi-layers, like here. There's more than, there's like 4 layers in there. And it needs high voltage, 50 to 150 volt. You could localize the response, meaning that you can have it bent at a certain location on that material. It doesn't have to be the entire surface. It has a very fast response, start and break time, and has very strong vibration. But it is a ceramic, so it's not very durable. It does tend to be brittle. After a certain amount of cycles of vibration, it will break. And another problem is it's got very high power consumption. So it takes a lot of energy to run a piezoceramic haptic device. But this is something new, where it's basically, it's called electroactive polymer. And it changes shape. So here's voltage off state of a material. The voltage on, it kind of just spreads out. It's very, very, it's elastic. So this is not a rigid material like the piezo ceramic. So this could be also very thin. It could be 200 microns thin. It's very elastic, it's very strong, but it's still relatively new, not very widely used. Some people are using this to create they create a surface where it feels like the buttons are coming out of the touch surface, and they're using something like a electroactive polymer. And it's really not that cheap. It's the cost that we're talking about is more expensive than, say, a ERM or LRA. So this is the one I'm really interested in. It's the most popular these days. It's called a linear resonant actuator. LRA is the formal term, and in fact it's just really a motor, a linear motor. It has a kind of a magnet here attached to a voice coil, and when the AC signal is sent into the actuator, it creates a movement of that magnetic mass. And it does only operate at a single frequency, but because it's an AC signal, you can control the amplitude of how much shaking it has. It has less power usage than the ERM, and like I said, you can modulate the amplitude and how much shaking it does. It's also very reliable, and it's low cost. So lots of these linear motors are being produced today. And here's the typical construction of a y-axis, so it's like perpendicular to what you're touching in terms of the surface. It has a spring, it's a moving mass, a voice coil. So in fact, it looks just like a speaker, the way it's designed. Here's the z-axis, so it's kind of a lateral movement motor. It's the same thing. Springs up here, down here. Here's a moving mass. Here's the voice coil. Again, not very different from a speaker. And this is the reason why SoundCheck is perfectly suited to measure a linear motor. So some of the performance differences we kind of talked about already. With the ERM, when you put the voltage in, it's going to go over overdrive, it's going to settle down, and when you stop, it's going to have this braking time to kind of stop spinning. So there's not really, the amplitude is not uniform, and also the time it takes to ramp up, to stop, is also longer. So the feedback is not sophisticated. Whereas you have a linear motor, the ramp up is shorter, and it has a pretty uniform feedback, and the braking is also faster than an ERM. And you can adjust the amplitude because it's an AC signal. So essentially, a linear motor is a high Q system, so it has a very strong resonance and across a very narrow frequency bandwidth. So all linear motors basically have a resonance, single peak, and that's where it's going to operate every time. And that's where the maximum output is, and it's also where the minimum power is required. And the typical frequency we're talking about for linear motors is around 175 to 235 hertz. Like I said, the strength of that vibration is actually adjustable. If you change the amplitude of the AC signal, you can get more or less vibration. And some of the things that you could do to control the, let's say, the braking time, you can actually do a 180-degree phase shift in your signal. That will also cut down on the braking time. So, what I'm going to do is demonstrate how do we measure a linear motor using SoundCheck. Software-wise, SoundCheck 14 or newer, and SoundCheck 15 now we actually have a unit of measurement for accelerometers. That's already built into SoundCheck. In SoundCheck 14, you could basically just create your own. But in 15, we have one ready-made for you. And we have different units of measurement based on what you're working with in terms of your actuator. In this sequence here, we have a listed amp connect, but in fact, instead of an amp connect, I just have the scamp, which is the same thing. It's a power amplifier with a reference resistor in it, so I can measure impedance. And we have an IAPE bias accelerometer from Buren Care. It's a 4519. And the test jig, you can see it here. Right now I don't have a Delrin, but I have a little aluminum block that I'm using. And I have a linear motor next to an accelerometer on the same block. And here's the setup. SoundCheck on my computer that Steve has been using all day. Here's my rig, my jig with the accelerometer next to the linear motor. And I have my power coming from the, right now it's a scamp instead of an amp connect, connected to the USB into the computer.
May I question?
Yes.
Would you previous please? Because I'm not good at accelerometer. How can accelerometer calibrate?
There's a calibrator for accelerometers.
What kind of calibrator?
Buren Care makes one. We didn't bring one today, but there is definitely a calibrator you can get for accelerometers.
Yeah. 4294.
I don't know.
It's basically a little shaker with a feedback loop.
Shaker.
Yeah, it's nice, but it's expensive.
Expensive?
Yeah, we have one in the Boston
Yeah.
office. Yeah. So, yeah, it's.
It puts out 1 G, 10 meters per second squared.
Right. So we could calibrate the accelerometer with the calibrator. We didn't have it.
You also have a calibration sequence in your system.
Not for the accelerometer, do we?
Well, for the calibration.
Yeah.
You could, when you do the demo, you can just show them the calibration.
Yeah, I can choose the calibration. So here's just kind of a quick overview of the sequence we've written for the linear motor. First step, we're going to kind of run a sweep, a sine sweep through the run the actuator with a sine sweep, and we're going to limit that range from 150 to 300 hertz because we don't know where the resonant frequency could be, and we'll actually calculate the fundamental, and this is built into SoundCheck. We could use the post-processing step to measure the resonant frequency, as well as F1 and F2, because some people want to know that value so they can plot their own curve. And then we could use that to also to calculate the electrical impedance of the motor. So from there we can get the resonant frequency, the Q, and the current drop. And then we're going to rerun the tests at that current frequency, the resonant frequency, and calculate the rise and the fall time, which is what also is interesting to people who are using linear motor. So this,
electric impedance is right or
Yeah,
right?
now we're actually measuring it.
we're measuring it through the reference resistor in the amplifier.
How
Just
many
like a loudspeaker measurement.
how many ohms are you using in sense register?
0.1.
Yeah,
0.1.
0.1.
I have another question.
Yes.
Would you please previous your measured data?
Oh,
Previous. Yes. Your resonance frequency is the peak point,
yes.
right? But your shape is asymmetry.
Yes.
Yeah, it's not so
Yes, so
It's
not symmetry. And how can you calculate your Q? Because I know normally
Oh, because of the
yeah,
speaker.
minus 3 dB point calculation method is based on symmetrical shape, but this is not
Symmetrical.
symmetrical. So how can you calculate the minus 3 dB point and Q?
Steve?
So this is actually measuring the acceleration. The impedance is will look more symmetric. When he does the demo, because there's two things being measured. There's the electrical impedance of the resonator, and I think you'll see that's more typical loudspeaker Q. And then there's this acceleration, which is really a what would we call it, like attack and release, like we do with hearing aids. This is more of a, how long does it take the linear motor to get up to full on,
Full on.
what you call braking,
Yeah.
braking something,
Yeah.
and then how quickly does it turn off. So you could think of that as sort of a impulse response. Two different things.
But it's the same. It should be the same frequency.
It's really a loudspeaker.
Yeah. So anyway, I want to just. So I'm going to run the sequence. So it's now here's your impedance, and that's more symmetrical.
Would you please enlarge?
Oh. So there's your impedance curve.
Okay, but exactly what's the specific word. But
Yeah, it's not
this
perfect.
shape can calculate Q.
Yeah.
So this is where you get the resonant frequency.
제가 왜 이야기를 하냐면 그러면 이게 대칭이 아니면 원래 마이너스 3dB 포인트에 각게 나와서 이렇게 해가지고 이제 Q 값을 정하는 건데 비대칭이면 구할 수가 없거든요. 스피커 같은 경우에는 이제 대칭이라는 가정하에서 이렇게 약간 보정을 해가지고 들어가는데 근데 이 그래프를 보니까 그래도 어느 정도 이제 대칭성이 유지가 되니까 대충 이제 커브 피팅을 해가지고 마이너스 3dB 포인트가 대충 쭉 따라가는 거예요. 절대적으로 이 커브 피팅을 따라가서는 Q를 찾을 수가 없죠.
There's two things that affect the why it's not perfect. One of them is the mass loading of the accelerometer. Is actually you got an accelerometer right next to this resonator, and really the accelerometer has its is causing some weight, added weight to the speaker.
Yeah.
Essentially, the other thing is we're just using beeswax, so the coupling is not perfect.
Yeah.
So if this was really ideal, you wouldn't see that funny shape. It would look more like a typical loudspeaker.
But typical loudspeaker also has inductance, so exactly it's not symmetry. Slightly shifted.
Yeah, you might have, yeah.
So in this sequence, get the frequency response or the estimated resonance, about 244 hertz. And here is the electrical measurement of the resonant frequency is 245. So we've taken the measurement. So let's go back. So we sweep it with this sign, this sweep, and then we figure out what the fundamental response. And we'll also use the impedance measurement right here to figure out what the impedance is, and then we have the resonant frequency. And then it's re-excited with a single tone at the resonant frequency to measure the rise and the fall time. And that's right here and here. So you have 7.85 milliseconds rise, 14.3 fall. And this is just an example sequence that's written in SoundCheck. So if you have an application related to linear motor and you already have a SoundCheck for other test and measurement applications, you can easily use this to also measure linear motor.
There are many kinds of haptic sensors.
Yes.
All kinds of haptic sensors use the same test chip.
Similar, I think that a lot of them use accelerometers, and that's no different than, it's just another transducer that we can connect to and measure.
Is this jig a worldwide standard or?
This is based on a
Data
Samsung specification
sheet. Yeah,
that we found.
yeah, Samsung published. This is how they measure it.
This is how the Samsung specification calls out the mass or the size of that jig and how it's.
This is all new to us.
So
The concept is
Other
simple.
companies use other test chip.
I really don't. The problem is that it doesn't get documented. Most of the time, you read the data sheet for the motor. They don't say what kind of test jig they put in.
yeah. Any questions? No, we still have time to spare.